Good morning. So, this particular lecture topic is regarding monitoring and control of hydrokinetic turbine. So, basically, when we talk about the monitoring and control, so we need to understand which parameter we would like to monitor and control. So, before going into that, I would like to discuss again some characteristics of this hydrokinetic turbine with different other renewable energy turbines. Then only you will be understanding that which are the parameter which is superior and which is useful or advantageous for this particular hydrokinetic turbine. So very common renewable energy generation system. One we have, if we consider this is a hydrokinetic turbine, another is solar and another is wind turbine. So we have we have analyzed these characteristics based on a few points. First one is the land requirement. So if you consider the land requirement for the hydrokinetic turbine, so very narrow space land is required for installation of the civil structure, which is required for the hydrokinetic turbine, mostly near the water source. Now, for solar energy, you have to have huge land cover so that you can install the solar panels. And wind energy also, there are lots of land cover is required because the total wind energy generation system, it will be installed on the land. So, land acquisition is a problem for solar and wind energy, but that will not be problem for the hydrokinetic turbine. But in other sense, when you are installing a hydrokinetic turbine, your land which is available near the water source, that must be proper to install that particular turbine. So the slope must be there, sufficient elevation must be there, or otherwise you need to excavate those parts in order to prepare this for the hydrokinetic turbine installation setup. Now, energy variation, how whenever it generate the energy, basically how they what is the frequency of this energy. So if you see the energy generation by this hydrokinetic turbine, it may be a continuous form of energy if water resources is available. But in case of the solar energy and in case of the wind energy, this is very much related with the availability of the solar radiation as well as availability of the wind velocity. So in this particular case, so what will happen, this hydrokinetic turbine that can be used to feed the base load demand, because we are assuming that we will be installing this hydrokinetic turbine for such a water resource system where 24 hours or 7 days in a week that particular water will be available. So continuous source of the supply of the energy is possible in case of hydrokinetic turbine, whereas this solar energy it can generate during the daytime, and wind energy it can be possible only when sufficient amount of the energy is fluid velocity is available. Not all the fluid velocity is sufficient to rotate that rotor of the wind turbine. Those things we will be discussing later, and from there itself we can derive which thing we need to monitor and control. Now, plant load factor, if you see the efficiency structure almost same for the hydrokinetic turbine as well as wind turbine, but solar energy, its efficiency will be some kind of less, almost 10%, 10 to 15% less compared to this hydrokinetic turbine and wind energy turbine. But the energy generation, if we consider the amount of the energy to be generated through the turbine, so then solar energy will be definitely better than the hydrokinetic turbine, and sometimes maybe from wind energy turbine. But that depends on the size of the energy generation system. So this particular comparison already we have discussed in the last class without this particular slide, that what will be the basic difference between the wind turbine and hydrokinetic turbine. Still I am telling you some of the points so that from this we can derive which particular things we need to control and monitor. So here we have seen that Reynolds number range for both this case, wind turbine and hydrokinetic turbine, it will be almost same. So the structure of the aerofoil or structure of the blade we can use same. but based on the possibility of the amount of the power generation, size may be differing. That is different issue. Now, for wind turbine, we are using compressible fluid, but compressibility effect will not be there. But in case of the hydrokinetic turbine, incompressible fluid will be there. Now, cavitation is not that much prominent problem in case of the wind turbine, but cavitation may be possible in case of the hydrokinetic turbine near the tip. So, the flow direction we have already discussed, that because the flow which we are getting for the hydrokinetic turbine, that is in a structured way. So, the flow direction it will be very much structured in case of the hydrokinetic turbine, but in case of the wind turbine it is random. That is the reason pitching arrangement and yawing arrangement is very much developed in case of the wind energy turbine, and those particular system is not that much available, and we do not incorporate in case of the hydrokinetic turbine, because in hydrokinetic turbine we know the direction of the fluid velocity is certain, from that which direction we will be getting the that particular fluid. So that yawing and pitching and that not that much importance, but still that can be incorporated in case of the hydrokinetic turbine. So that is one criteria where we can do the monitoring and the control. Obviously, the velocity, amount of the velocity, that is another criteria where we would like to control or monitor so these two parameters we would like to control. Now, some of the things, that flow variation, just I told you, that is also most important, because flow variation we have discussed last class, and during the material selection also, the flow duration have an impact of the blade and the structure of the turbine, so it will have the impact on the failure criteria. So those things also is very much important. So those are the factors basically we need to monitor as well as control. So again, I would like to show you some of the pictures where in general this hydrokinetic turbine can be installed. Thermal power plant, their pipeline is there, so you can use some in-pipe hydropower turbine. Check dams, already you have seen. Tail race of the hydropower plant. So in the tail race also you will find that after releasing the water, there are huge amount of the water source available. Tidal current turbine, in tidal current, during the tidal, what will happen, you may get 5 meter per second of velocity of the water in the channel or in a canal or in the connection between this your river and the sea. There those type of almost up to 5 meter per second. So there you can install this type of hydrokinetic turbine. So during different types of, there are different types of tide. So during different types of tide, you can say, for example, ebb tide. So you can find out that you can install those particular turbine in order to harness the energy. So those are the structure. It will come under the tidal turbine, but the design will be of the hydrokinetic turbine. Cooling channel, the same. Sewage treatment plant, you can put the turbine inside the pipeline. Irrigation canal, there you can get the clean water, because usually in irrigation channel we never use the water which will be corroding, which will have the corrosive property. So their irrigation channel you will get the clean water, so those impurity or chemical properties problem will not be there. So easily we can put the turbines here in this particular channel. Again in the sea, in the deep sea, there also we can put the hydrokinetic turbine. How? So there are some structure can be made which will create some elevation difference, and then also we can put the this hydrokinetic turbine model. So those are the different studies, and that will come under the ocean energy converter system. But still the ocean energy converting system that incorporates conventional energy, hydro turbine as well as this hydrokinetic turbine. So different type of hydrokinetic turbine application exists. Now I will show you, I promised you I will show you different commercially available models of the hydrokinetic turbine. So here I have given you example, and this I have taken from a review paper, review of hydrokinetic turbines and enhancement technique for canal installation. This particular paper from here, there I have, this is available in the internet, you can also download. So here I have taken these pictures. So you can see this is a turbine and there are few components. There is a float and there is a diffuser. So we can understand this is the inlet side and that is the exit side. So diffuser is actually a diverging section. So this is the generator which is installed. There is the rotor, and this is the debris protection kind of strainer. Now you can see the smaller size of the debris that will be arrested in this particular part. Bigger size of debris or impurities or some other things which is floating or carrying with the water, maybe some part of the broken tree, so that will be arrested here. So those things is the problem for hydrokinetic turbine, which will not be problem in case of the solar as well as in case of the wind turbine. So differences, their advantage and disadvantage always will be there. What is the characteristics of this particular turbine? This particular turbine is axial flow turbine. So now if you see what is given here, there is a velocity. This particular turbine is designed with respect to the velocity. They have made the survey, and after that they come up with to a conclusion that 2.8 meter per second, that may be a constant resource. Maybe through flow duration curve we have discussed in the last class. And then they have found out this particular single unit, it can produce 5 kilowatt of energy. So, and it is having a 1 meter of diameter. So this is the structure, one structure. Again, debris protection unit that is given here. This is also axial flow turbine, and this is for with respect to 3.1 meter per second. It is also giving 5 kilowatt of energy with 1 meter of diameter. Now this is Hydroquest River 1.4 cross flow. This is cross flow type of turbine. This is axial flow. This is cross flow type of turbine. This cross flow type of turbine, it is producing 40 kilowatt. Anyway, for this in this particular figure, the diameter information is not provided. So you can cross check this particular literature if that is provided here. So here this power is more with respect to the power of the previous one. That doesn't mean that this is more efficient. It may have the bigger dimension. So this is a apparently it is looking like there is a deflector installed here. Apparently it is looking deflector installed here, and it is a vertical axis turbine. So vertical axis but cross flow turbine. So we have discussed those classification last class. So here is another type of cross flow type of turbine, but Savonius type. If you see the blade, here one blade like this, another is S type. Maybe this is a 3-blade type. So by observing from the outside, it is not possible to tell, but we can assume that it may be 2-blade or 3-blade. It appears to be 3-blade because the angle maybe 2 or 3-blade. So Savonius type of turbine. This is again another axial flow turbine. Now if you see this structure, this axial flow turbine, so there is a capsule sort of part. So maybe this there is a bevel gear arrangement inside it, so that the rotation of the shaft, it can be transferred like this. So we have discussed in the last class, because the whole system, it will be immersed into the water. Here also whole system, that whole system means up to this part it will be immersed into the water. This is the only floating device. So here the structure indicates that this will be installed inside the water, but with the self weight it will be somehow stuck in the river bed. So there is no floating part is available here. So and there are also floating part available, these two, 1 and 2. But here if you see this is the vertical axis, maybe H radius type of turbine. H radius, it is structure is kind of H, English letter H. So here if you see this is the generator, there is the bearing part. If you require, you can install some of the gear box also in between these two, shaft and this gearbox, so that its speed, rotational speed will be increased. So those type of modification you can do. So here you can see this is a Darius type, helical Darius type, but it is a horizontal axis. So far we have seen, if there is a Darius type, that is a vertical axis. I have shown you the picture last day. Here it is a horizontal axis turbine. So horizontal axis turbine, and we have found out a vertical axis turbine. This is also cross flow turbine. This is also cross flow type of turbine, but it is a multi-blade. This is drag blade turbine. So it is a modified Savonius. Means Savonius, there may be 2, 3, 4 maximum. It is more. So this is now placed on the bottom of the river bed, and maybe this is anchored with the rock bed formation which is formed inside the rock. So different type of turbine. This is a vertical axis turbine, but this is having a cross section of we can assume this is a aerofoil cross section, so it will be lift based turbine. So based on this, there are different classification. There may be some other modification. And this is the frame we have discussed. That frame will be installed with the civil structure in the two banks. One bank will be here in the left side, another will be here in the left side, and middle it will carry the this particular turbine. So different type of arrangement will be there. So these are the example. Now, if you see this particular curve here, this particular curve is called power density curve. The power density curve, it indicates blue one is for the water turbine, this red one, this is for the wind turbine. So the few curves we have taken, again references are given. So how do you read this particular curve? Say you require a power density. What is the unit of power density? Watt per meter square. What is this meter square? Meter square indicates the area of the diameter corresponding to the diameter of the that particular turbine. So power density, suppose if you require something watt, say 500 watt per meter square area. So I can draw a line here, and correspondingly I can draw another line in the vertical. So what will happen if I go for the 500 watt per meter square? I will get a point here somewhere around 2 meter per second velocity. So 2 meter per second of velocity in the water, it can produce 500 water per meter square. Per meter square, that means we are basically assuming, say that size of this particular turbine, if we fix say 10 meter square, or say 2 meter square is the size of this turbine, both turbine, wind turbine as well as the water turbine. So then if I would like to generate 500 watt, then for the water I require only 2 meter per second, but for air I require almost 13 meter per second of velocity. So it actually depends on the density of the fluid. If you remember the formula, 1 by 2 rho A V cube. So that V cube will be applied, but rho here it is changing, 1000 time differences is there. So in this particular manner, basically you will be finding this type of two different curve for the two types of turbine. So anyway, so there are different comparison, different sort of representation is there in order to compare. Now, whenever you are going for designing of or planning for any turbine system, so you must have some design phase, you must have some installation phase, and again you must have some maintenance and control stage. So first you will be assuming, and these things also we have discussed, we will be assuming, estimating the original resources of the energy. Then corresponding to that, you will find out some of the parts of the turbine, you will go for the modeling of the turbine. Then installation will come. Suppose you have considered the turbine, you have already designed. Now whenever you are going to install, so civil structure will come. So where you will be installing, whether that particular area is suitable for installing those particular turbine or not, whether some civil construction is required or not. So all these things you have to do, and after that monitoring. So we have calculated everything based on some uncertain thing. That means the natural resources. We have taken some data for a few years, we have analyzed it statistically, and then we came up with a conclusion. But that doesn't guarantee that it will be certain. Always it will be very, that particular value will be available. So those uncertain thing you need to monitor, and accordingly you have to control the system. As well as there may be some cases where failure may be occurring, as well as suddenly something may come up. So all these things, for all these things you require monitoring and control. So before going into that, if you, we want to tell you another some classification, some comparison between horizontal axis turbine and vertical axis turbine, mostly on the hydrokinetic. So horizontal axis turbine, basically in order to start the horizontal axis turbine, approximately 0.5 meter per second velocity is sufficient. That means the less amount of the velocity is sufficient to run the horizontal axis turbine. And the vertical axis turbine, the value is bigger, means it is not mandatory or fixed that it must require 1 meter per second. It can be done. Again, that will be depends on the size of the turbine, material of the turbine, whether the turbine material is heavy weight or less weight. So it depends. But these two value will show you certain idea that horizontal axis turbine requires lesser amount of the velocity to start with, but vertical axis turbine require higher amount of the energy. Similarly, the TSR, you can see the maximum TSR, the efficiency curve is inverted bell shape. So inverted bell shape, we always try to run our turbine surrounding the maximum efficiency zone. So the maximum efficiency, people have observed so many performance curve of so many different types of turbine, and they come to the conclusion that maximum TSR value for this horizontal axis turbine, it will be around 4.5, and definitely that will be for lift based turbine, because drag based turbine it will be around 1, and for lift based turbine, this vertical axis turbine, it will be around 3. So this type of comparison also represents that horizontal axis turbine, it will be rotating faster. So that is why the velocity requirement also lesser. So with a lesser velocity, it will rotate. With a similar velocity, it will rotate faster. So this comparison you will understand. Now, water to wear efficiency, that means water energy is available, I am converting into mechanical energy through the turbine, and then it will be converting into the electricity energy from mechanical energy to electricity energy generator, through generator. So this conversion, ultimately total overall conversion capacity is around 25%, both are same. Difference is not that much. Debris resistance capacity is comparatively less in the horizontal axis turbine, and rotor simplicity in case of the horizontal axis turbine, it will be a bit of complex, but still these are very abstract comparison. You cannot generalize it. And material quality and is costing, it will be less, and this will be more. And platoon or floating device, smaller and compactness is there in case of the horizontal axis turbine, and larger in case of the vertical axis turbine, because you need to support vertical axis turbine. Already I have told you, horizontal axis turbine you will get two support, one is here, another is here. Vertical axis turbine, it will be hanging, so its support requirement is higher, and again it's there will be lots of unbalances forces which will be acting on the bearing where it will be housed. So all those problems will be, you have to taken care of while you are installing such type of turbine. As well as wherever there is special care is required, there is a probability of the failure, and those things you need to monitor and control. So that is the reason we have discussed so many things. Now, if we see this particular curve, this is a power versus flow speed curve. Corresponding to flow speed, what will be the power? So this particular line, it actually shows corresponding to the Bell's limit. Bell's limit is the ideal value, 0.593, approximate 60%. We have already discussed. So we always try to improve the performance of our turbine so that it will become closer to the Bell's limit. So it will not happen. So the curve we will be getting for some normal turbine, normal means in case of our hydrokinetic turbine or wind turbine, because both have been, is applicable for the Bell's limit. Say it is this particular curve. So this particular curve, what is the difference between this particular curve and this particular curve? So this is the area 1, say area 2. So this area 1 and area 2 is the differences between these two curves. Somehow if we minimize, we can minimize the area, those area under the curve, so that I can uplift the design of a performance of my turbine towards the Bell's limit. So when in general we try to do some optimization calculation for a particular turbine, so in general we give the objective function such a manner that we calculate this area and we represent it through the sum of the equation, and then we try to minimize those particular equation value with certain constant. So this is the optimization structure with which will be associated with some of the variables. Now you decide variables, and we define this particular curve with respect to the variable. That variable may be design variable, this variable may be operating variable, and then you have constructed and representing your system. Now this system will giving you this system should represent this particular line. Now differences between these two also you have to represent, and that particular difference through this particular area you need to give for the minimization. Minimization, now you do for minimization, you adjust the value, parameter value, and then you will come up with certain value. That particular value if you implement on your design, so that will the optimized value for this particular turbine. So this would be the concept. So for this, what may happen, somebody may change the pitch angle, somebody may change some, incorporate some of the additional parts, deflector, and some of the channel modification, say narrowing down or some other things, or maybe uplifting of the bed, so that the ultimate velocity you are obtaining exactly at the turbine blade, it will be higher. So those things, those type of modification, channel modification, turbine blade modification, turbine plate modification, maybe turbine stage modification, that means different stage you are using different type of blades. So there are different modification prescribed by different researchers. So those things are there. So now, site selection, and so what are the things? So we require a steep section, we require a flume section, we require siphoning or pipe section, and robust canal, so that we can implement our turbines in order to get highest amount of the output. So those are the things, as well as you have to find out what is the electricity demand, what is the transmission length. If transmission length is more, and complex mean it will be traveling over a few area which is not accessible, so then the transmission loss will be there. So the electricity which is producing, and whenever it is reaching to the consumer, it may lost. So all these things you have to keep it in your mind when you are going for a installation of a plant. Okay, now, so we have seen which are the parameters coming in front of us when we are discussing about the performance of the turbine. Now we will see the which type of parameters we will be monitoring, when monitoring, and how we will be monitoring, and obviously how it will be controlling. So first of all, turbine, whenever turbine will start running, on turbine it will stop, whether turbine speed will be increasing, turbine speed will be decreasing, ultimately it will be producing the electricity. So for this, governing mechanism will be there. Conventional governing mechanism you may have read, but this type of governing mechanism, that means basically you have to change the angle, pitch angle of this blade. And in case of the wind turbine, there are different mechanism. Yaw mechanism is there, but for our turbine, hydrokinetic turbine, that is not required. But some of the tilting of the blade, that may be possible, but most of the cases we found out that the blades are engineerily been fixed. But adjusting type of blade in case of the water turbine, it engineerally not been observed, because there are some other issue. Because if you put some controlling part in this particular to adjust the pitch angle of this blade, so it may happen that water is directly carrying some impurities, or maybe some parts, some broken tree, maybe something. So it may clog those particular systems. So in generally, people try to keep it fixed, but still this governing mechanism, that means you can control the entrance of the fluid inside the cavity. So you have seen that there was a diverging section, converging section. So if those type of duct or cavity, inside the cavity you are putting your turbine, so then there you can put some flap, and you can control the entrance of the fluid, entry of the fluid at the entrance of the turbine. So in that manner you can govern the particular turbine. Power control system, in the whenever turbine is basically generating the electricity, say you have developed your turbine for a particular amount of the velocity, suddenly you have found out the river stream or the stream of the canal that is having a high velocity. So if you run with this particular high velocity, then there may be possibility of failure. So you must have some controlling technique, so that you can either stop the turbine or you can uplift the turbine. So the part which is coming under the electrical engineering, so we can call this is a power control system, or whether the amount of the electricity there has been produced, how to distribute those things, whether to switch on, whether to switch off. So those things, all these things will come under the power control system. Monitoring. So not only this part, that means how much is the velocity right now in the river, how much is the electricity demand, how much is what is the situation of the aquatic life, what is the situation of the debris, that means continuous monitoring of the silt. So all these things, all the parameter which are basically influencing the operation of the turbine or maybe efficiency of the turbine. So those things can be monitored with different device. So those different device will come under the monitoring. So just I have told you that the peaking of the fluid velocity inside the channel or peak electricity production or maybe your velocity has been increased or decreased, or maybe you are changing your site because this type of turbine is very light, so you can put it somewhere else also where maybe for a particular season you may not get the electricity. So maybe you would like to shift those particular energy generation part, that means turbine station, maybe some kilometer downstream. So those things if you want to do, so you can go for the velocity correction. And now I just told you there are different living being. That means not only whenever we are talking about the hydrokinetic turbine, it will be installed on the river. That may be installed in the tidal stream. That may be installed in the ocean also. I just told you, I have just shown you few photographs. So those things, those particular sites are actually is floating. So that particular part also can be moved. So maybe during that movement, or maybe during that particular site, in this particular site, some aquatic life may encounter with these particular devices. So then you have to ensure the safety of this particular aquatic lives. So that is also engineerily being done with this hydrokinetic turbine, because hydrokinetic turbine is a very small structure. Maximum it will be a few meter, not more than 2-3 meters. So it will not hamper those aquatic life as such. But if we talk about some other tidal generation unit, that may be bigger. So although this is a concern criteria, but that will not be that much harmful. That is why you can tell this is a environment friendly device, so which is basically generating the energy. Okay. Now along with this, some environmental monitoring. Environmental monitoring here, now it will come as a precipitation. Suppose you are going for harnessing the energy for a particular river, and that catchment of the river in this particular catchment, just like today suddenly early morning rain started. So that was unexpected. In this particular season, rainfall cannot be happening. So this, due to the rainfall, sudden rainfall, it may happen, it can accumulate the water and it can feed the river where you have installed your turbine. This is a flash flood kind of thing. So it can make some damage. So those things, if it is happening, so early monitoring system definitely before 2-3 hours. Nowadays, our satellite image is very much powerful. So it will give you the idea, and accordingly you can go for the some corrective measure to prevent those particular situations. So this is for that environmental monitoring. So structure of the turbine design. So I told you that this type of turbine, it is very much prone to the failure due to the fatigue failure, or maybe it may be clogged, or maybe it may have some other problem towards the failure. Cavitation problem may occur. So this failure you can observe through the strain gauge, or maybe some other monitoring system which is happening surrounding this particular turbine. You can put some underwater camera inside this surrounding this particular site, which can give you live feed what is happening surrounding the turbine. Or maybe this turbine has been stopped. We will not always talk about the failure. We may talk about the shutdown of our power plant. So we have installed, we have invested our money to generate the energy. So what will happen if your turbine gets shut down? So we need to run it again. So for this particular, you need to have some constant monitoring. So we can do some constant monitoring through the underwater camera, or maybe from drone system. Drone system, we cannot run the drone constantly, but you can put your underwater camera constantly. So if some of the unit of your turbine system it is being stuck, you can identify the problem and you can do the corrective measure. So that kind of system must also be there. Electrical system, so you should have some voltage and current measurement. So voltmeter, current meter sort of thing you should have. Grid connection, whether grid connection is working properly or not. So power controlling unit that must be installed near your hydrokinetic turbine energy system. And if you are storing your energy to a battery, so those measurement, those monitoring system also must be there. So this type of power unit system you can find out. So power control system, startup sequence, so different type of MCB, load control system, control to design CCD network. So different type of things can be installed for the controlling of the hydrokinetic turbine system, and that is applicable for any small hydropower system. So those are common. Now just we discussed, pitch control may be required, so torque control may be required, that means rotation of the turbine. So you can divert some of the water. If suppose inflow energy is higher, you have suddenly got the information that huge amount of the water is coming into my river, so you must have certain civil structure upstream of the site, so that if required I can divert the water, so that I can allow certain amount of the water only to my power station. So those things you have to do, as well as sometimes I can stop the turbine, so I can uplift the turbine. You can uplift the turbine vertically, you can uplift the turbine just like by tilting, just coming out of the river water. So individually you can do, with all set you can do. So those particular system you must have if you are spending so much of money, and if you are concerned about your each and every unit. Emergency stop, that also that particular aspect also should be present in your controlling unit. So overload protection, that also can be, overload protection is present in case of our household engineering also. Similar type of protection must be there in case of the this particular system. Fault diagnosis, that means you will be you can do different type of fault diagnosis, whether this is electrical fault, whether it is a mechanical fault. Mechanical fault you can go with the, means if breakage issue will be there, so crack issue will be there, so you can go with the strain gauge, so you will get an early detection idea that this is going to be break. Redundancy, that means if you should have some backup plan if some of the turbine is not working, so you must have some backup unit so that you can replace the particular rotor, so that it can give you the constant output out of this particular power station. So those things also there. So these are the some devices which will be required to monitor all these things. So this is a SCADA system. So this data acquisition system actually will record different types of parameters. Now you will decide which type of parameter you require. If you want to require torque, so it will use the torque meter, and it can feed to the SCADA system. If you require some vibration amplitude, so it will be feed to the SCADA system. SCADA system, it will acquire all the information through different measuring probes. So measuring probes will be there. If this particular SCADA system or DAC system that is compatible with this particular code, then you can feed the data to this particular SCADA system. It will give you data maybe 0.01 with respect to each 0.01 second. So you will be basically deciding what will be the interval of the data system. Now with this particular data, you can train your system. That means you can train your machine learning or artificial intelligence system. They will be, after they will be trained, so they will give you some early fault detection signal. So whether something is happening in your bearing, so some unusual noise is coming or not, whether something happened in your turbine, so whenever it is rotating, so vibration is occurring. So whether velocity you are getting in the upstream, that is fluctuating or not, and whether the pressure surrounding this particular turbine, if you would like to take the pressure value, whether it is changing or not. So all these values will be given, will be fed to your system. So, and this is a typical structure of the SCADA system. So many parameters are fed, and if you set the threshold value, so definitely that can give you the warning, and that warning can be in terms of the color. It may be red, or maybe it can create the noise. So that will be based on the capacity of the software of this particular SCADA system. So there are some advanced system. So that particular data, whatever I have told you, that is the live system. Live data, it will be occurring, or maybe data will be recorded in this particular system. Later on you can access. That is one thing. Another is IoT system, Internet of Things system. So this SCADA system incorporating with the IoT system, the data can be stored in a cloud and it can give you simultaneously through the internet. So those things also can be happening. So it's up to you. That means it's up to the owner of this particular power plant how much money they will be investing. So that much money they will be investing. So what is their expectation? How much power they actually want to be generated, so that will be basically they will be given to the consumer and that will be sold. So revenue must be sufficient. Then only that type of energy can be implemented. So technology is there, but unless or until it is economically friendly or economically viable, so no technology can be implemented. Technology is there. So here this is the current meter, this is the flow meter. Already I have shown you an analog accelerometer. So with this you can measure some of other variables. Strain gauge, this is underwater camera, this is electric current meter, this is handheld electric current meter, volt current, all the values related to electricity you can measure. But if you are installing a power plant, so then basically you have to use the control panel. So those values will be available. So I will show you some of the examples. So these are the parameters you need to remember. I will show you few examples. Few examples I have taken. I have given the reference here. So one example, this has been basically implemented at TRL 8 level, technology readiness level. There are few technology readiness level up to 9. So technology readiness level, it is a implementation level. So you can go, you can search for TRL in the internet also. So you will get from 1, 2, 3, 4, 5, 6, 7, 8 different stages of technology. The technology first conceptualization, then you will be doing the calculation, then you will be planning for something, designing the model, simulating, and then you will go for laboratory experiment. And then if laboratory experiment is successful, you will install it in a real field, but will be in smaller project, it will be pilot project. Then if it is actually working, then you can plan for the bigger one, and that will be in the around this technology readiness level 7 and 8. So after that, basically it will produce the revenue. So it will be implemented in a mass scale. So technology readiness level, they have done some exercise, and this particular exercise is made by IIT Roorkee as well as CHTTC Canada. So I have got this photograph, I have made some collage. So here you can see velocity measurement maybe at the initial level on a canal, and then they have designed some rotor, they have simulated that particular rotor, then they have go for the manufacturing, and then they have done some prototype testing. You may find out that turbine design is something different. I have taken few photographs, I have put it here. And then it has been implemented for maybe for the power production. So these are the stages already we have discussed. So this will be some features here, and your references are there from where I have got it. So similar type of things. This is another control of hydrokinetic turbine. So you can see this is a vertical axis H type of turbine, HDDS type of turbine. So this is the real one. You can see this is the drive shaft bearing is here, and here is the gearbox, and at the end this is the generator. So far I have already told the sequence. So, and this is the floating device. So this is the carriage. Basically this carriage will be installed with a car, and it will be bring to the field. Then this particular floating or pontoon, this will be installed. I have already show you those chart. So it will be installed here on the river. So it will be floating and it will be giving the result output. So this is actually will be floating. So and now this floating device can be anchored through some mooring, either from the riverbed or from the bank of the river. Because this floating devices has been given because they are not at all, they do not wish to depend on the water level. So if water level goes down, so all the system will goes down. And if water level goes up, so all the system will goes up. So this is another modification. But if you are fixing some rod, so it will happen that particular frame, so that particular river flow should be controlled, because you have to keep certain amount of the water inside the river. So which type of river you are dealing with, based on this your turbine design also will change. Here you can see the turbine power output corresponding to the RPM with different river velocity or maybe channel velocity. So 2 meter per second it is giving this type of, 2.5 meter second it is giving the pink, so 3 meter per second it is giving the yellow. And what the thing you will be observing, you can observe that the topmost river power, the highest turbine power, that is corresponding to a certain velocity, that particular thing it is shifting. Top power value, that is shifting with different river velocity, so it will be shifting in the right. So those type of characteristics also you can see. Now if I am with a similar velocity, if I increase the turbine diameter, so what will happen? It may happen that the particular topmost value, top load power generation value, it may be here corresponding to a certain RPM, and only thing that the curve will be getting due to the bigger size of diameter, it may happen it will be almost along the single line. So that you have to check. So which type of nature of the curve it will be producing, because of the change in diameter, or because of the change in river velocity, or because of the implementation of the some of the techniques which will enhance the flow. So those things will be there. So this is another chart I have actually taken from some other source. So they are actually gone for the tidal current or maybe ocean current. So there they have checked for lobster, they have checked for the health of the fish, marine mammals, and marine sound acoustics, sea birds. So these are their parameters to monitor. So they would like to monitor the health of the lobster, fish, marine mammals, marine sounds, whether that particular sounds it is being generated from the turbine which will be affecting the marine life or not. So those are basically related to the marine turbine. Again, that marine turbine we can use the hydrokinetic turbine system. So where, in which site you are installing your turbine, based on this your control and monitoring system may be modified. So these are the 3 or 4 type of example I have shown you. So I hope I will show you some more case study, and sir also show you, Professor Mamdud also show you some of the case study. You will get some other idea also. So how basically different factors are associated with the power generation of the turbine. So if you have any question, you can ask. Okay, you think about this, and if you have anything, any queries, and we can discuss in tomorrow's last session, second half, there is a discussion session, there also you can ask other questions. Okay, thank you.